How's it going, everyone? I'm checking out some homework stuff right now, waiting for everybody else to get here.
Good morning, Professor.
How's it going?
Doing pretty well. How about you?
All right. I'm looking at our homework assignments. I'm inclined to leave it as it is, but I want to double check what chapter 9 is looking like right now. It's a lot different a second ago. There's no chapter 9 conceptual. That's what I'm looking for. All right, now I've done it. Okay. So it looks like I'm still waiting for people to come in. I just changed the dates for chapter 9, conceptual, and chapter 9 problems. All are due on 3/31, which is the same day that your test is due. So you've got a test that opened up, 2 or 3 days ago, and that's due for chat, and that covers chapter 9. That's why I went ahead and made all the homeworks due on the same date roughly. Actually, let me go back. I don't like that. I'm going to set the homeworks due to a couple of days later, but you really, the point of doing the homework is that you have it done before the test. I'm going to give you a couple extra days to do the homework beyond the test day. But I'm just doing that so you don't feel overwhelmed with how much work you got to do. You really need to go ahead and knock this homework out immediately and then do the test shortly thereafter for best results. So I'm going to make it 4/4 for both the, well, I'll leave the conceptual due on 3/31, and I'll say 4/4 will be the chapter 9 homework. So the conceptual is due on 3/31, and the actual mathematical problems for chapter 9 are due on April 4th. So I would definitely do as much of that before you take the test as you can, especially the homework part, because that's really what the majority of the homework question or the test questions are, is your ability to solve mathematical problems, word problems, if you will, of a physics variety. So all the chapters that I make that are extra credit, they'll have the word extra credit on them. So you'll see they're all posted right now. And the ones that end in the word extra credit are the ones. So let me look at what that is. Right now, I have just 12, 13, and 41 as extra credit. Chapters 12, 13, and 41 is extra credit right now. Man, it's a small number of people showing up. We got like 45 students in the class. I only got like 27 here. I guess we should press on. So what we have now is we started into chapter 9. We've done collisions. I've given you a ton of examples through my YouTube channel. I've done links to those on the actual Canvas page that goes links to my YouTube channel where I've done some pretty neat examples. This chapter is not only about conservation of momentum, it's also about the center of mass system. So we have to be able to calculate centers of mass. We have to be able to do conservation of momentum, stuff like that. I wanted to give you a couple other problems. You can see some really good examples of that when you're doing when you're looking at the examples on my YouTube channel. But really, you'll get plenty of practice between that and looking at my homeworks. One thing your book does that's really nice is it actually works out the details of an elastic collision in one dimension. This is an important thing for well, basically just for collisions in general. So let me start off by explaining that to you. So when you have a collision, normally the biggest forces in the actual collision are the forces between the two objects that collided. And if that's the case, then you can sort of ignore, say, the little bit of friction between the tires and the cars, at least for an instant, and then, get an idea of what the velocities would be immediately after the collision, and then use the forces of friction that are associated with the tires sliding on the road to see how far they'll move, and that sort of stuff. And that's a pretty coherent, meaningful, useful application of science to a car collision, for instance. But the big deal is, mainly from Newton's second law, the total force is equal to dp dt, where dp dt is the derivative of momentum with respect to time. If that total force is equal to zero, which, like I said, is, ideally it really is zero, but in some cases it can just be that the major forces are so much bigger than the minor forces that you can ignore those minor forces like friction compared to the force of collision of one car into another, in which case you can still treat it as dp dt equals zero, because the net force is zero, dp dt equals zero, and since dp dt equals zero, that means the momentum is a constant. Later, we'll learn that when you treat an object like something other than a particle, then you can sort of set up a F equals ma for each little particle. Let's say if we're treating this pin, we can divide this up into individual atoms and do a F equals ma for each of those. And what you find out is there's a F equals ma for the center of mass of this particle. And then there's a F equals ma for sort of all the for sort of the rotation of the particle about the center of mass. And because of that, you can basically treat the whole system as if it's one big F equals ma. And then you get that even though it's not point particles, we can apply this to several particles at once. So when I say the momentum is a constant, that might mean P1 M1, or excuse me, M1 V1 plus M2 V2 plus M3 V3 for each of the particles, M1, M2, and M3, right? Where V is a vector in each case. All of that adds up to a constant before the collision. Then all of that after the collision adds up to the same constant, M1 V1 final plus M2 V2 final plus M3 V3 final. That's the big deal. That's how we do this collision thing. What I'm going to do is give you sort of the results that your book does and explains how they get them. I might even derive it. I don't know, see how I feel like when I'm doing it. It's been a while since I've done this derivation. I think I haven't done it for a year. So if it starts to get hairy where I'm screwing up, then I'll just abort. But basically what we have is the summation of forces. Let me turn on my document cam. We know from Newton's second law in this new form that we weren't used to, Newton's second law says the total force is equal to dp dt, where dp dt is, of course, the derivative of momentum with respect to time. If the summation of forces is equal to zero, in other words, the total force equals zero, then dp dt is equal to zero, which means P is equal to a constant. That's conservation of momentum, period, right? Now, again, like I told you, this F equals dp dt can be applied per particle, or you can apply it as a system and realize that the system, say this pin, has a mv for this particle in the pin, an mv for this particle in the pin, an mv for this particle in the pin, an mv for this part, all the other particles. So all of these add up in this part, and then you get the total P, m1 times v1 plus m2 times v2 plus m3 times v3. All that stuff is equal to zero. Remember, of course, the definition of momentum is mass times velocity. Now what we're going to do is we're going to imagine an elastic collision, which I talked about before. That implies that kinetic energy is equal to a constant. So let's imagine for a second two particles moving in a line. Okay, so I'm going to say here's a particle A and here's a particle B. This is moving at velocity VB, and this one's moving at velocity VA. And of course, this is MA, and this is MB, right? So conservation of momentum which is really that, gives us MAVA plus MBVB is equal to, after the collision, what we assume is going to happen is VA and VB are going to be moving off in opposite directions. VA prime and VB prime, so that we have MAVA prime plus MBVB prime. That's conservation of momentum. That's a done deal. Now, the fact that it's one-dimensional means I can get rid of all the vector signs and just say MAVA plus MBVB equals MAVA prime plus MBVB prime. Now, notice when I do it this way, as I did up there, everything was positive. So obviously, we expect some of these V's to come out negative, because obviously we're going to have to choose one direction, say the right, to be positive, in which case VA is positive and VB prime is positive, but VB is negative and VA prime would be negative. So all that will come out in the math, but this is one of our equations. I'll call that equation 1. Now, kinetic energy equals a constant gives us another scenario. This scenario is 1/2 MAVA squared plus 1/2 MBVB squared is equal to 1/2 MA, or big A, sorry, VA prime squared plus 1/2 MBVB prime squared. Okay, that's another equation. We can go ahead and call that equation 2 if we want. Now, if I take equation 1 and get all the stuff related to mass A on one side and then all the stuff with mass B on the other side, then I can get the following. So I'm going to take MA and say M times A, or M sub A. I have to multiply that by VA, so that's going to be VA. And then, of course, this is also multiplied by VA, or by MA. So I'm going to write minus VA prime like this. And then the other side, I'll write MB. And then, of course, on this side, I have VB prime is positive. And if I pull that over there, that becomes minus VB. So this one's initial minus final, and that one's final minus initial. And I will call this 1 prime. That's what that equation is. Okay. Now, if I write the kinetic energy similarly, meaning I only have the VAs, or excuse me, all the VAs with only MA and all the VBs with only VBs, I can get something quite easy. In fact, first off, I'll multiply by 2 because everything has a 1/2 in it, so that makes life a little easier. When I do this, I'm going to say 2 is going to give me MA. Now I've got a parentheses VA squared minus VA prime squared. And then on the other side, I'll get MB times, again, in this case, it's VB prime minus VB squared. I'll call this equation 2 prime. Okay, now if I want to, I can recall from my rules of factoring that A squared minus B squared is A minus B times A plus B. So I can make this equation 2 prime a little nicer. I will rewrite 2 prime, maybe I'll call it 2 double prime. Now it's going to be MA times VA minus VA prime times VA plus VA prime is equal to MB times VB, times VB prime minus VB times VB prime plus VB. So that's equation 2 prime.
Can you bring that a
Now
little
we've
closer?
gotten basically the ability. Go ahead.
Can you bring that a little closer? It's pretty blurry.
Yes. Now what I'm going to do is take equation 2 prime and divide it by equation 1 prime.
Where
So
you get VA plus
2
VB?
prime. Go ahead, Lauren.
Where you get the VA plus VA primes and the VB plus VB prime?
This is the definition of a difference of squares. Remember from algebra, a squared minus b squared is a minus b times a plus b.
Yep.
So I just factored this into VA minus VA prime times VA plus VA prime.
So once you take out the MA, that's
So
what it
now I'm going
splits
to
up into?
divide. I don't understand the way you asked that question.
No, I was wondering how, I understand how you got
This.
VA. Oh, wait, no, I see it now because it's squared.
Did you? Gotcha. Yeah. The difference of squares is basically factors into plus or minus the square roots. All right, so now I'm going to divide 2 prime by 1 prime. And I think you see what happens. Basically, this 2 prime has a MA VA minus VA prime. So that's going to completely cancel out, and I'll just get VA plus VA prime. And this one, of course, has a MB VB prime minus VB. So that's all going to cancel out this, and that'll just leave me VB prime plus VB. So I'll get basically VA plus VA prime is equal to VB prime plus VB. Okay. Now I can subtract that such that I have, let's do VA minus VB. So I'll say VA minus VB is equal to, so I pulled this one over here. So that one over there is going to become VB prime minus VA prime. Double checking. I've got VA minus VB is equal to VB prime minus VA. I can make this look a little better by writing VA minus VB is equal to the negative of VA, dang it, negative of VA prime minus VB prime. The reason that looks better is A minus B, right? This is the before, this is the after, and they just basically are the opposite order. That's the difference. This equation is a important keeper. I will rewrite it since I made a boo-boo on that one. VA minus VB, so that's the initial velocities, becomes the negative of the final velocities in the same order. So this is a big result that you get for one-dimensional motion that is elastic collision. That is an elastic one-dimensional collision. So momentum has been conserved, and also kinetic energy has been conserved. So if you want to see what happens now, we can say, well, what if MA and MB are actually equal to each other? Well, in that case, really, you don't have anything special from this equation. And by the way, this equation, I think your book labeled 9-8. So that is one you can actually use when you're doing your test. In other words, that's one of the ones you can put on your equation sheet. We already discussed the case of 2 identical masses running into each other. But now we have basically the scenario if two identical masses, again, notice this equation is completely independent of the masses. We've gotten rid of all that stuff, but this equation stands all on its own. So if I take the case of a cue ball running into another ball, so let's say a cue ball strikes, whoa, I'm now spelling strike with a V instead of a K in there, strikes a resting 8 ball. What are the outcomes in one dimension? In other words, if you strike it head on, it's got to be one dimensional. So this is you hitting usually a cue ball properly. There are some instances where you don't want to hit square on, obviously. Just go, for instance, if you want to knock an 8 ball into a side pocket that is literally just a little bit off to the left of, then you hit your cue ball on the left-hand side of the 8 ball, and hopefully you hit it at such an angle that it causes it to go into the side pocket. This is a head-on collision, though. So what I'm going to do is I'm going to say the velocity of the cue ball, there's the cue ball, here's the 8 ball, VB is equal to 0, VA is just equal to V, and this is the 8 ball, so I'll color it black. Then after the collision, I've got some motion going on here. And what I want to find out is, what is that motion? Well, according to this, VA minus VB is equal to negative VA prime minus VB prime. In parentheses, don't forget that, that's a critical. So now we've got a scenario where VB is actually equal to 0. So we know now that V is equal to negative VA prime plus VB prime. Okay. So with that in mind, what's going to possibly happen? Well, there's two scenarios. Either VB leaves with the exact same velocity, so that's one scenario. VB prime, the velocity of the cue ball after the collision, will be the exact same velocity the cue ball had before the collision. That's that Newton's cradle case that I just mentioned. And then, of course, the cue ball will be sitting still. But another scenario, check this out. This one's kind of crazy. The other scenario is, what if VB was 0? Then VA would spontaneously have to be negative V. Now, that doesn't happen in most scenarios, so you really know that the answer is this. You could also, remember we did this earlier for two-dimensional case, and we found the scenario was that they leave at 90-degree angles, which is obviously two-dimensional. But the other scenario was that basically the same thing, V equals VB prime, so the cue ball leaves with the same velocity the other one had, and VA is equal to 0. So that's basically one example. Any questions on that? It's kind of just reinforcing what we did. Now, obviously, another example is that VA is equal to, or VA prime is actually equal to negative V. And VB prime is equal to 0. Well, what that means is that basically you could actually picture this in such a scenario that it completely missed, in which case the velocity of the ball keeps moving on at velocity V. So that's another scenario that it fits. Now, let's examine this other case in some more extreme situations. If you want to go back and consider unequal masses, for instance, you can say, let's say we have a particle let's call this M. I guess I'll go ahead and stick with MA and MB. So this will be MA, and it's moving at a velocity VA, and it's going to run into another mass, MB, where this time the velocity VB is equal to 0. And I'm going to say it's a elastic collision. So this is example 2, elastic collision. So we know that VA minus VB equals negative VA prime minus VB prime. We know that actually works, right? Because it's an elastic collision. It just has to be a special case. But we know some other stuff too. So let's take, for instance, conservation of momentum. I've got MA times VA is equal to MA VA prime plus MB VB prime. That's another scenario we could actually get. And in fact, we could take this and say, well, MB times VB prime, in this scenario, I solved for that. That ends up giving me MA times VA minus VA prime, like that. So I've now got that velocity, or that relationship. If kinetic energy is conserved, then we can use this scenario, which in the case of VB equals 0, gives us that VA is equal to negative VA prime plus VB prime. Or solving for VA prime, because that's the thing we don't know. We're pretending as if we know MA, VA, and MB, right? Of course, we also know VB prime, VB. But if I want to solve this for VA prime, I would say VA prime is clearly equal to, pull it over this side, and I'm going to get VB prime minus VA. So this is another equation I managed to figure out. So I can actually combine these two and solve for VB prime. I can say VB prime is equal to, I'm going to put this over here and say MA over MB, whoa, it times VA minus VA prime. But I found out a result for VA prime, so I can say MA over MB. Again, just solving for this. Now I plug in place of VA prime, I'm going to plug in this VA that I found up here. So I'll do VA minus, remember there's a minus in front of this VA prime, so I really should make this a square bracket and put a parenthesis here. And now I'm going to say VB prime minus VA. I can continue on. I'll get MA over MB times, now carrying out all this distributive property for the negative, I get VA minus VB prime plus VA. Obviously, that's MA over MB times 2VA minus VB prime. I can distribute that, and in fact, I will go like this. I'll multiply this MB again. So I'll say now MB VB prime is equal to 2MA VA, that's something we know, minus MB VB prime. So now I can take this term and bring it over there, and I'll get MB times VB prime plus VB prime is equal to 2MA VA. Making sure I haven't made any mistakes. I feel like I did somewhere. Let's see. This is MA over MB. That came from that. That looks good to me. VA minus VA prime, that looks good. VA prime turned out to be VB prime minus VA. I agree with that. VA prime turned out to be VB prime minus VA. I plugged that in there. That'd be VA minus VB prime plus VA. Oh, yeah, plus VA. So it'd be 2 VA. So now it looks like I'm getting 2 MB VB prime is equal to 2 MA VA. Or basically VB prime is equal to VA. That was not what I expected. Well, I mean, it is what I expected because it's the same thing I got in the other one, that VA prime or VB prime was equal to VA. Because of that, we can then go back and say, okay, well, evidently from this equation, since VB prime is equal to VA, this must be equal to 0. So that would make the same scenario we did before. But I was trying to get the more general cases, what happened if they don't combine. So this is one result. That we had already found. Well, I shouldn't write it here as found. So now let's try to look for the other result that we might have found. So if we take this equation right here, the VA prime is equal to VB minus VA, I can put that back into the momentum equation and let's see what happens. So that was one result. It happened to be the result that I wasn't searching for. So let me try to go for it another way. Now that I've found this result up here, everybody see that VA prime equals VB prime minus VA? I'm going to put that off to the side. VA prime is equal to VB prime minus VA. Again, this is only for the case where the ball was the target ball was not initially moving. So VB is just equal to 0. Now I'm going to say MAVA is equal to MAVA prime plus MBVB prime. That's what I want them to do. This is again from conservation of momentum. It's exactly that equation right there. Now I'm going to plug this into that. Okay. So when I plug that into that, we should be able to get something. I'm going to take this VA prime and replace it with that. So now I'm going to have MAVA is equal to MA times VB prime minus VA. That's just that term, but I have plus a MB VB prime. So now I'll write it again. So I'll put a comma, MAVA, make sure, ran out of paper again, ran out of the camera again. MAVA is equal to, now I'm going to distribute MA VB prime minus MAVA plus, that's the second term. Now this term over here would be plus MBVB prime. So what I'm going to try to solve for is VB prime and then VA prime. So let's do VB prime first. I can group these two, this VB prime and this VB prime. That's going to give me VB prime times, since it's on this side, I'll pull it over to this side. That'll make this a negative and that a positive. So I'm going to do VB prime, or excuse me, MB. No, since I'm pulling it over here, this will be negative. This one will be, this one that is positive is going to become negative, and this one that is positive is going to become, oh, they're both going to be negative. That's why. Okay, they're the same sign over here, so they'll become negative on that side. I'll just leave it on this side since they're both negative. I thought I was going to get rid of a negative that way, but I'm not. So on this side, I've got an MB, and I also have a plus MA. So that's just this term and this term. Now I'll pull this one over to here. That'll be a MA VA plus a MA VA. So you could really do it like that, but I think you can already see what's going to happen. That's just going to give you a 2. So ultimately I say VB, and this is going to be familiar for you. So this is actually worthwhile because it's going to look just like our Atwood machine. And that's the whole purpose of doing this derivation, is we get a formula that we can use over and over again for our one-dimensional head-on collision that looks like a formula we've already had before. So this is going to become 2 MAVA. That looks just like the formula for tension in the Atwood machine, over MA plus MB. So I'll say this looks like tension in Atwood. Yeah, remember the Atwood machine we did? Or do you even remember what the Atwood machine was? Yeah, it was the pulley, and you had a mass and a mass. And what we got was the acceleration was the difference of the masses divided by the sum of the masses times G. That was the acceleration. It turned out the tension was 2 times the product of the masses times G over the sum. So this has got a 2, not times the product of the masses, just one of the masses times V over that. So it does look like the tension formula. Now that I have that, I can also plug this back in and use it to solve for VA prime. So what we're going to do next is solve for VA prime. And if I choose to do that, say from this equation, VA prime is equal to VB prime minus VA, I can say VA prime is equal to VB prime minus VA. That means VA prime is equal to 2 MA over MA plus MB. All that times VA, that's what VB prime is from there, minus VA. Now to get a common denominator, I need to multiply this VA by MA plus MB over MA plus MB. Did somebody else just come in? I heard a beep. No. Okay. So now I can do that, and I think you'll see what happens. This one is a 2 MAVA minus MAVA, so that's going to make that just 1 MAVA. And then I've got a minus MBVA. So it's basically just going to be MA minus MB over MA plus MB, all that times VB. So ultimately, my result is VA prime is equal to MA minus MB over MA plus MB times VA. Okay, which I could also write this one as 2 MA over MA plus MB times VA. When you write it stuff like this, basically you have some number that's unitless times the thing that has the units that you want. So it's sometimes nicer to write it this way, and that's exactly the same thing I did here. I've got a unitless quantity multiplied by a quantity that has the units I want, so you can immediately see that the units work out. And lo and behold, this looks just like the tension, or excuse me, the acceleration in the Atwood machine. The difference being this would be G and this would be A, the acceleration, and this would be gravitational acceleration. So those are general results of when a moving body hits a body sitting still in an elastic collision. And it has some pretty extreme scenarios that are pretty useful. And I think you've probably seen it on Wipeout before. If any of y'all ever watched Wipeout, it's a fun show watching people get the crap kicked out of them by gravity and a lack of knowledge of physics. or just being caught off guard is probably the more important thing. So let's examine this. I've got what I found was just like the tension. I'll write this tension up here. Atwood machine. So the Atwood machine has A equals M. Let's call it MA minus MB over MA plus MB times G. And then I also had T is equal to 2 MA over MA plus MB times MB G. Right? So there's your Atwood machine. Whereas here is your target particle. We have V A prime, the final velocity of the second particle. That was the second thing we derived. So that was MA minus MB over MA plus MB times VA. And then we found the target's velocity to be 2MA over MA plus MB times VA. So I think that sort of shows you the parallel that I was talking about. So now let's imagine a case where A is much, much greater than MB. In other words, the particle that's moving is super, super heavy. So this is a Mack truck hitting a guy on a bike. Or a car hitting this is a really sad scenario. A car hitting a motorcycle is like this as well. What you do to examine this is you take the limit as, let's say, MA or MB over MA approaches 0. So this could be taken as the limit as MB over MA approaches 0. That's one way of looking at it. It's just a limit. So let's look at this. Let's look at what happens to VB prime. So the limit of MB over MA approaching 0 of 2MA over MA plus MB VA. Well, what I'm going to do to make this happen is I'm going to multiply by 1 over MA, both top and bottom. So I'll do 1 over MA over 1 over MA. Since I did the same thing to the top and the bottom, I'm just multiplying by 1, so I haven't really changed anything. So now I have the limit as MB over MA approaches 0. This becomes 2 over, when the MA over hits the 1 over MA, this just becomes 1. And this becomes MB over MA. And then everything else is times VA. So I think you can see as this approaches 0, this becomes twice the velocity of the impactor. This is why it's so dangerous, being a motorcycle rider. If you get hit by a car, your mass is insignificant compared to that of a car or a truck or something like that. If someone hits you and you're sitting still, you're literally going to leave. If they're going 60 miles per hour, you're going to leave your motorcycle, or you and your motorcycle are going to be traveling at 120. That's not a good scenario. So that's the difference of a big mass hitting a little mass. Now let's consider a small mass hitting a big mass. So now I'm going to say MA is much less than MB. In other words, this is a fly hitting a windshield. So that's one scenario, a fly running into a car windshield. obviously the fly is going to bounce off. And of course, obviously a fly is actually going to absorb quite a bit of the energy with his body crushing and stuff like that. So it's not that good of an elastic collision, but it's the same scenario with a BB being shot at, say, Superman. Okay. So we can still work that out. I'm again going to take the limit this time as MA over MB approaches 0 of, now I'm going to do the velocity VA. Well, the velocity VA prime is equal to MA. This one, by the way, was VB prime. VA prime is MA minus MB over MA plus MB times VA. And this, of course, is equal to the limit as MA over MB approaches 0. I'm going to multiply this by, of course, 1 over MB over 1 over MB. So this will become MA over MB minus 1 over MA over MB plus 1. All that times VA. And I think you can tell as this goes to 0, this is just going to become negative VA. So if a small object hits a really big object, it's basically going to leave with the exact same velocity that it had initially. That's a big deal. I mean, for the person running into it. In fact, this is not unlike what happened to me when I was at NC State. I was working on a master's in structural engineering, and I was also trying to regain my fitness because I'd been lifting weights a lot, but I broke my back and had to take some time off. Then I busted my knee and had to have knee surgery. So between all that, I gained quite a bit of weight. So I was out at the track one day and I'm running, and I decided to walk off across the track, and I'm looking across the other side of the track because I just finished talking to this dude who's literally got one leg. He's got one of those grasshopper sort of prosthetic things, you know, the I don't want to share that. The prosthetic that they have that's like made out of fiberglass and Kevlar and shaped like that. There's this dude with one leg and he's running on the track like that. And I just asked him what he got in the 100-yard dash or the 100-meter, and he was like 12.9 seconds. And I watched him in time, and I was like, wow, that's 12.9 seconds. I can't do that. I was getting like 14, right? And, you know, this is my fastest time. So I'm sitting there watching this guy, and I walk out onto the track. Well, all of a sudden, I feel something in my peripheral going, boop, 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 boop. And I look, and there's friggin' inside linebacker for NC State's football team. I recognized his face as I was seeing blood. He was coming into the side of me and just ran to me. I'm a big guy, and at that time I was maybe 230, but this dude's like 290. And he rams into me, and I was real worried because I screwed up, so I didn't want him to hurt himself. So I grabbed him and gave him a sweet little hug to protect him as he busted my kidney and made me pee blood for 2 weeks. So basically what happened was I got hit by a Mack truck, and I left with twice his velocity. It was pretty fun. So anyways, I'll just leave that as a little humorous anecdote for you to consider as opposed to the normal boring stuff that we do. Now, we've done basically various collisions. I've committed to you some of the things you can do with momentum. There's even problems that you can solve where things get really, really nasty. And I took the time to solve all that. So if you look at collisions in 2 and 3 dimensions, you'll see an example 9-12. This is just a big algebraic nightmare generally, but example 9-12 and 9-13, you should look over. All it says is, hey, momentum before the collision equals momentum after the collision. If one body is moving, or if they're both moving, you know, along the same line, then you're lucky enough to not have any y components of momentum initially. And that means the y components of momentum afterwards, which are done by, again, taking sines and cosines of the angle, multiplying that sine or cosine times the m times v, and that'll get you the x component or the y component. You got to account for one direction being positive and the other direction being negative. but it's a real nightmare to try to solve that system of equations. I took the time to actually solve that for you once and for all in my YouTube video. That's way more complicated even than that little stuff I just did there for one dimension. But I gave you a sort of formula that works that will allow you to solve those two-dimensional two-body problems. So I definitely want you to check that out. What I'm going to do right now is show you a ballistic pendulum, and then I'm going to introduce you to the center of mass, which is a whole nother cool scenario. So let's imagine we want to figure out how fast a bullet is when it leaves the muzzle of a gun, okay? So let's say we fire a little m with a big velocity v, okay? So I got this itty bitty bullet of mass m moving with a velocity v, okay? What I'm going to do is I'm going to let that bullet embed itself into a big mass, big M, okay? And then that big mass, big M, is going to go from there, where it was, in other words, up to some new height, like this, by it being on a pendulum system where basically this now comes over to here and this now comes to there. So you can see it sort of swung around like that, right? So first off, we do conservation of momentum. So P equals a constant implies that little mv is equal to little m plus big M. Notice they're stuck together now because the bullet's actually inside of there. You assume very little mass was lost, right? So they're now one object whose mass is m plus m, and it's now moving with a small velocity v, okay? We can see now that that velocity v is equal to m over m plus big M times the big V. And that's really what we want. We want to know what the muzzle velocity is. So big V is equal to question mark. Well, now what we know is energy is conserved. In some sense, you're going to lose some of this to heat and stuff like that. But in principle, you should be able to say that the kinetic energy of the bullet, 1/2 little m big V squared, is equal to the potential energy of this block plus the bullet. So that's m plus big M times G times big H is what I said earlier. So now I should be able to say that V, I can put this in here by computing what this was. And I can say, for instance, 1/2 m V squared. I'll plug in, let's see, m plus m over little m times little v, that squared is equal to m plus big M. Actually, I don't think that works out very well. That's not giving me the solution that I want. Let's see here. I got that. Okay. Yeah, I think that still works. The problem is I'm not going to know little v, and I don't want to know little v. All I want to know is big V in terms of G, right?
Is that G
So
times
I
big
should
M,
be
or
able to.
is that G
What's that
times
now?
is that G times big M or G times H?
That's an 8, sorry.
Okay.
Yeah,
Thanks.
that's basically this side where I plugged in all this stuff. When I do this, this is just going to give me the little v, and I don't really want the little v. I want the big V, but I know what the little v is, so that could help. Let's just start, because I don't think that's panning out. Let's solve this for H, or no, let's solve this for big V. So I'll say multiply through by 2, and then divide through by M. I'll get 2m plus M times G times big H over little m is equal to big V squared. Okay. Now, that actually gives it to me. That's all I need. So V, the muzzle velocity, is what I really wanted. the muzzle velocity will actually be given by the square root of 2 times m plus m over little m times g times h. If I wanted to know specifically this velocity the ball had before, I mean the block and mass had, I also can now do that. I would say little v is equal to m over m plus m times now the square root of 2 m plus m over m gh. But if I pull this m and m over m plus m inside, it becomes squared. So it will actually cancel out, and I'll get v is equal to 2 square root 2 m over m plus m times g times h. So that's the other answer. So I think that's pretty good. The fact that I went off here didn't really matter, didn't harm us. But the big thing was I had enough right here to figure out the muzzle velocity of the gun just by solving this for v, because there was no other constants. It turns out to be that. But it's kind of neat how the velocity of the block in them is literally the same thing, but you replace m plus m over m with m over m plus m. So that's kind of neat. That's another neat problem. I'll call that one, say, number 3, and this one number 4. Now, the last thing we're going to do is talk about center of mass. And the center of mass is the point that when you're actually going to attack, say, a physics problem with F equals ma, and you're dealing with an actual physical object like a cell phone or a pen, you know, if I throw this pen, you know it's going to do this sort of loopy thing, but it's going to go in a parabola because we learned that projectile motion makes parabolas. But what part of this pin goes in the actual path of a parabola happens to be the center of mass of it. Okay, the center of mass happens to be the point over my finger where I can center, where I can put this pin and have it reach equilibrium. So obviously my center of mass is somewhere along this line. Now, in principle, from symmetry, we know that the center of mass is also along this line. If I turn that 90 degrees, it's also along that line. So we know it's along the center of the axis of symmetry of this, and then right about there. So that's the center of mass. Well, how do we put that in words? Well, the x center of mass, you can imagine it applying a torque, and the torque would be, say, one particle times its distance from the origin, so m1, x1. If I multiply that by g, I would actually get a torque. Torque is force, mg, times lever arm, which would be x1, right? Now, if I take the other one and do the same thing, that'd be m2, x2, and continue on, m3, x3, plus ... plus mn, xn for n particular particles. Now I've got all the torques, but I need to divide that by the sum of the masses. So I need to divide that by m1 plus m2 plus m3 plus ... plus mn, right? And that one thing gives it the units, but it also takes into account getting rid of the mass part that sort of overweighs it. So this is the actual formula for the center of mass in terms of x. If you had a y, if it was in 2 dimensions, you do the same thing with y center of mass, and you replace this x with a y1, y2, so on and so forth, right? And if you had a z, you do the same thing as well. So that type of problem is really easy. You can use that, for instance, to calculate the center of mass of the Earth-Moon system by just imagining the moon with a little m and the Earth with a big M. And let's say this right here, the center of the Earth is the origin. And let's say this is the y-axis and this is the x-axis. So we'd say the x center of mass for the Earth-Moon system would be the mass of the Earth times 0, because its center of mass is right at the center of the Earth, plus the mass of the moon times the distance to the moon, over the mass of the Earth plus the mass of the moon. When you do that, you get the mass of the moon happens to be 7.35 times 10 to the 22. The distance between the Earth and moon happens to be 384 or 3.84 times 10 to the 5th kilometers.
Can you bring it in a little closer?
Yeah. And this came from the front cover of your book. 3.84 times 10 to the 5th kilometers. It's okay to use in kilometers because I'll just get the result in kilometers. And then I'll divide that by the mass of the Earth, which is, or by the mass of the moon plus the mass of the Earth. I'll leave the unit off on that one because it's getting kind of hairy. The mass of the Earth, on the other hand, is 5.98 times 10 to the 24th. All that's in kilograms. So again, I'll put that up top there. Notice that unit in the bottom is a kilogram that I wrote off to the side. If you actually do this, what you'll find is about 7/8 of the distance out from the center of the Earth towards the Earth radius. So the center of mass of the Earth-Moon system is actually inside of the Earth. And that's the point that actually follows an elliptical orbit. It's kind of neat to do that. Here, I'll go ahead and calculate it. 7.35 e to the 22 times 3.84 e to the 5 divided by, I'll use parentheses here, 7.35 e to the 22 plus 5.98 e to the 24. That gives me 4.66 times 10 to the 3rd kilometers. Almost kilograms there. Kilometers. And the radius of the Earth, which is given this symbol, the radius of the Earth, notice, happens to be 6.38 times 10 to the, if I keep it in kilometers to compare apples to apples, it's 6.38 times 10 to the 3rd kilometers. So 4.66 divided by 6.38 gives me about 73%. So literally you go out 0.73 of the Earth's radius right about there, say that's the center of mass of the Earth-Moon system. That's the point that's actually doing an elliptical orbit. And the center of the moon is going woo, 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 like that, okay? So that's a simple center of mass. A bigger one, we go to 11 to 12, 15. Now, if you actually have to deal with discrete bodies as opposed to little individual masses, obviously the little individual masses are a lot easier, but we can actually do a distribution of mass as well. So let's imagine this. Let's imagine an XY coordinate system, X, Y. I'm going to put a triangle up here. And let's say that's a 45-degree triangle. So this is 45 degrees here. And let's say its total mass is big M. And of course, this dimension would be A. And since that's a 45-degree angle, this dimension must also be A. Okay. Well, the equivalent of this in integral form is X CM is equal to the integral of X dm over the integral of dm. Okay. So if I want the X center of mass, I want to know where along this X I should balance this block with my finger, right? It's some fraction of A. So what I'm going to do is try to have a constant X. In other words, I'm going to take a differential element who only differs in x by an infinitesimal amount. So what I'll use is my dm would be this little block right here. So this little thing right here is dm, and I'm going to call that basically dx times rho times the volume. So I'm going to say rho times dv, because rho would be the density of the object. And by the way, in this case, I'm really using more like a sigma because it's a two-dimensional lamina. So sigma is like rho, which is really the mass divided by the area in this case. So I would say the total m divided by 1/2 a squared is what that density is. And that works out pretty good. I know I wrote that in orange, so let me put it up here so y'all can see it. I said this rho type thing, since it's what we call a homogeneous lamina, I'm basically saying it's mass per unit area, not mass per unit length. If I wanted to do three-dimensional, it wouldn't be much harder to do it. I just call that m over L times 1/2 a squared, where L is the thickness. Okay. But the volume, of course, is dx times basically the y. And of course, this y function, you might realize, is y equals 1 times x. That's the definition of a 45-degree angle, is the equation y equals x is a line that's equal to that. So what I'm going to say is this is rho, which is that number right there, no big deal, times x, because y equals x. It's technically y. Okay, but I'm using the fact that y equals x for this expression, times dx. So that's what my dm is. So now I can integrate and say x, the integral of x dm is actually the integral from x equals 0 to a of rho times x. There's already an x there, so that'd be x squared dx, which equals rho times 1/3 a cubed. So this answer is going to be rho 1/3 rho times a cubed. And of course, the integral of dm is going to be equal to the integral from x equals 0 to a of rho x dx, which equals rho times 1/2 a squared. So XCM, and if you've had your statics class already, you probably already know how to figure out the center of mass. It's supposed to be 1/3 of the way from the thickest part, so it should be 2/3 a roughly. I'm going to go ahead and put this in here. The top part was 1/3 rho a cubed. The bottom part was 1/2 rho a squared. So clearly the cube cancels out with the square down here, just leaving an a. The rho cancels out with that, and I get, lo and behold, exactly what I just told you, 2/3 a. Now the y center of mass is the same thing. YCM is equal to the integral of y dm over the integral of dm. In this case, maybe I will use this as my dm. And of course, in that case, it's again going to be rho times dv, but I'm going to say it's x units wide, but this equation really is y equals x, so I can say that's going to be y times dy. Okay. So as I integrate, actually, this one should be, actually, it should be a minus that, right? That would be dm, but the distance, a minus, yeah, I think that should be a minus y. Everybody see why that is? The distance from here to here, this is A, and this is X. So it's A minus X. So it should be A minus Y here. Because it's technically A minus X, but X is equal to Y because that's the expression. So I'm going to do the top will be the integral of Y times rho times A minus Y times dy for that. All of this will be the integral of rho times A minus Y dy. The rho can come out in front in both cases, and they've already canceled each other out. Boom, boom. And now I've got the integral of AY minus y squared dy. The rho came out front, so AY minus y squared. Okay, that looks good. Over the integral of A minus y dy. I don't know why I switched to writing in orange, but I did for a second there. So this is going to become the integral from y equals 0 to A, y equals 0 to A. When I integrate that, AY becomes 1/2 A y squared minus 1/3 y cubed over AY minus 1/2 y squared. Both of these evaluated from 0 to A, 0 to A. That's going to give me 1/2 A cubed minus 1/3 A cubed over A squared minus 1/2 A squared. 1/2 and 1/3 has a common denominator of 6, so that'd be 3/6 minus 2/6 would be 1/6 A cubed over this would be 2/2 minus 1/2, which would be 1/2 A squared. So this becomes, in fact, 2/3 A, which is also what we expect. Well, actually, that should be 1/3. 2/6. Oh, yeah. 2/6 would be 1/3. Sorry. I would carry the next step. Equals 2/6 times A, which is obviously 1/3 A. I knew it had to be that because it's got to be towards the fatter end. The fatter end is this side, so it's got to be 1/3 of the way down, or 2/3 of the way from the top, or 1/3 of the way up. So that's exactly it. The center of mass for this triangle is 2/3 A, 1/3 A, and that's it in a nutshell. Okay. So it turns out, and here's the way all this comes together. If the net force is 0 on a system, we already found from Newton's second law that the net force means the momentum equals 0. So the summation of the forces is equal to dp dt says the summation forces equals 0 implies P equals a constant. Okay. But now what I'm going to tell you is that the summation of the forces equals 0 also means the summation of forces equals m d2x over dt squared, where x is a vector representing the position. That's also equal to 0. So that means that the position's not going to move. So that means xcm dot would equal 0. So xcm does not move.
Can you bring that closer so it's a little more clear?
Yeah, it's a little hard to read. That's because mainly I was banking on the words. So what I'm saying is there's two ways of looking at a total force being equal to zero. You can say, oh, well, the total force being equal to zero means that the momentum is constant, is conserved. But you can also realize, wait a second, if the total force on a system is equal to zero, then the center of mass can't move. Now it can rotate all at once about that center of mass, and there's a way for us to detect whether that's happening, but that requires us to introduce the concept of torque. But other than that, really the big deal is the center of mass can't move. So that's why if you look in the examples that I have in Canvas, where I fired that cannon inside of a train car, you can do that as conservation of momentum, meaning the cannon and train car will recoil with a certain velocity when the cannon ball is shot out with another velocity. And then that train car will move with that constant velocity as long as the ball doesn't hit the other side. But the instant the ball hits the other side, the momentum that the ball has will cancel out the momentum that the cannon has, because it's still the same momentum because it was conserved. So the cannon will come to a stop, as will the ball. I mean, as will the train car, and you will calculate that new location of the train car by how far it traveled with that new velocity for that amount of time. Now you can also, that's with conservation of momentum. Now you can also just calculate the center of mass of the system with the cannon and the ball on the left-hand side, and then calculate where the center of mass of the car is with the cannonball on the other side. And the difference in those center of masses will exactly be the distance that the train car moved in this case. So by using the fact that the center of mass can't move, you would predict that the train car moved by the exact same distance. So that's why we cover these two things in the same section. And this is a very typical integral type problem you should be expected to be able to do for chapter 9. We've now finished chapter 9, which is why I think chapter 9 test is due Wednesday. Notice that gives you, or excuse me, due Wednesday at midnight. Notice that still gives you Tuesday to ask me any lingering questions. Of course, it gives you a chance to ask me questions by email. Speaking of which, Lauren, I did get your email. That's why I was taking care of some stuff this morning. And you probably noticed at the beginning that I did change those dates. But anyways, I got all weekend for you to ask me questions about chapter 9, but the test is already there. You should start taking the practice test, and when you feel like you've gotten enough either practice from that or the homework, then take the real test. You get, I think, 3 attempts. I might have did 4 on this one, I can't remember, but it says so on what it is when you start to take it. I've already moderated them for people that have extensions and time. Everybody, of course, make sure you get your test done on time. I did set a due date so you can get the warning from Canvas, but you're free to go other than that. I will wait for the last person to leave in case y'all have any questions. Man, we only had 25 people show up out of, or 26 people show up out of 40. So.
Thank you. Have a good one.
Rosa, Brett, Kyrie, sorry, that's what it is, Kyrie. Any of y'all have any questions?
I do not.
A homework question.
All right. Well, you folks have a good weekend. Thanks for coming.
Professor.
Happy physicking.
Professor.
Yes, Lauren, go ahead.
I had a homework question.
Okay, go for it.
I'm gonna find it real
Let
quick.
me make it so you can share your screen. I hit the wrong button, dang it. Dang it, hit it again. Why do these things keep happening to me? Okay, you should be able to share now, Lauren. to bring it back while you're pulling that up. Lukewarm coffee. You find it yet, Lauren? Why we're waiting for that, Rosa or Brett? Do y'all have any questions?
Taking forever
I
to
think they
load.
might
I'm
be
in a different
gone.
room. Okay. Like I was able to get all of these by myself, but I needed help trying to find that one. But I don't really know how it came out to be that.
Okay, let me see. Chuck and Jackie stand on separate carts, both of which can slide without friction. The combined mass of Chuck and his cart, M cart, is identical to the combined mass of Jackie and her cart initially. Or excuse me, in her cart. Initially, Chuck and Jackie and their carts are at rest. So the total momentum before collision, before anything, is actually 0. That's important to know. Chuck then picks up a ball of mass, M ball, and throws it to Jackie, who catches it. Assume the ball travels in a straight line parallel to the ground, ignoring the effect of gravity. After Chuck throws the ball, his speed relative to the ground is VC. The speed of the ball of the thrown ball relative to the ground is VB. Jackie catches the ball when it reaches her, and she and her cart begin to move. Jackie's speed relative to the ground after she catches the ball is VJ. When answering the questions in the problem, keep the following in mind. The original mass, M cart, of Chuck and his cart does not include the mass of the ball. Okay. And the speed of an object is the magnitude of its velocity. An object speed will always be a non-negative quantity. Okay. So this part E is what you're having problems with, you say? Find
Yes.
Jackie's speed. Okay, so what we're going to do is, first off, we're going to take conservation of momentum. We know that P initial is equal to 0. What that means is when he throws the ball, then 0 is equal to the mass of him in the cart, which is M cart, times the velocity, which they said was V. After Chuck throws the ball, his speed relative to the ground is VC. And they're wanting that to be a negative. So I'm going to say that's negative VC. So that VC comes out positive, in other words. So I'm saying Chuck is throwing the ball to the right, and that means the cart and him should go to the left. And then I'll say plus the mass of the ball times the velocity of the ball relative to the ground, which is VB. So that's what we know so far is that, and then we're wanting her VJ, so we'll know that. All right, let's stop you sharing your screen real quick, and I'll show you what I'm writing down over here. So the total momentum before, since nobody's moving, the total momentum must be 0. Let me make that a little better by. That's still not good. There it is. Okay, so the initial momentum of the whole system is 0, so the left-hand side 0. What I'm saying is after he throws the ball, he's moving relative to the ground at a velocity VC, or with a speed VC, but it's in the negative direction, so I'll put a negative there, and the ball is moving to the right at a velocity VB, and now that means that we can relate the two. We can say basically that the velocity of the ball is equal to the mass of the cart over the mass of the ball times the velocity of the cart or chuck. Okay, so we've got that part for starters. Now what happens is we then have conservation of momentum still, which is that basically the mass of the ball, which would be m ball, times VB. That's the total momentum. Just looking at her and the ball, her initially momentum is 0. She's sitting perfectly still. So for them, P initial is equal to 0. Well, actually, P initial is not equal to 0. I'll say P initial for her is this. It's the mass of the velocity, or the mass of the ball times the velocity of the ball. And that's equal to now the mass of the ball plus the mass of Jill. Did they call that MJ for Jill in her cart, or was that was there a mass at all for Jill in her cart? I'm assuming it's going to be MJ.
No, majority of the question just really just solve for variable. With variables, there ain't no really numbers.
Okay, but did they give a symbol for the mass of her and her cart? I just want to make sure I don't use the wrong symbol.
No, it's just M cart and the M ball. But you are solving
Okay.
for VJ.
All right, so
which is
this,
velocity.
they said they were identical, right?
Yes.
Yeah, I think they said that her and her cart and Chuck and his cart are identical. So I'm just going to call this cart again. Okay. That's going to leave with a velocity VJ, which is basically Jill's velocity. That's what we're trying to find. So now if I solve for VJ, I see VJ is going to be M ball over M ball plus M cart times VB. But notice VB is M cart over M ball times VC. So I am getting M ball, that's going to cancel out with the M ball, and I'm going to get M cart over M ball plus M cart times VC. I guess in principle, we could have left it. That's not what they had, right? They had M cart times M ball or something like that, or did they have M ball cart squared?
Yeah. I couldn't figure out how they got it to be squared.
Yeah, show me the thing again, the problem again, please. VC. Okay, Chuck and Jack are separate carts, both of which can slide without friction. The combined mass of Chuck and his cart is identical to the combined. Okay, so I did get that part right, that the combined mass of Jackie and her cart are the same thing. And their carts are at rest. Okay, Chuck then pulls up, picks up the ball, throws it M ball. Okay, so they got M cart times M ball. Oh, U was a big thing. U is, what was U?
Representative, the relative speed. Yeah, the relative speed.
The relative speed with
I
respect
mean, yeah. You gotta use
but it's
wherever U is
the relative speed of what?
relative speed of,
Okay, U is equal to VB plus VC.
and it's the relative speed to the ground. I'm pretty sure you had to solve for VB. So I'm pretty sure the equation would be like
Gotcha.
VB
Okay, I
equals,
see. The U is supposed to be the velocity of the cart plus the velocity of the ball.
velocity of the cart
Okay,
plus
I
the
see.
velocity of the ball.
Yeah, that's what U is. So that's where that other term's coming from. If you take the velocity U is equal to velocity of B plus velocity of cart, you'll say U is equal to VB, which we got as M cart over M ball times VC. Now I'm going to say plus VC, but VC, I need to get a common denominator. So I'm going to say M ball over M ball times VC. So now you can say, if I want that, I can now say in terms of U, U is equal to M cart plus M ball over M ball times V cart. So that means V cart is equal to M ball, that's where it came from, over M cart plus M ball times U. So now I can plug that in and I get VJ is equal to M cart times M ball times U over, notice M ball plus M cart is squared now, so I get M ball plus M cart squared. So that's
Okay.
how they got that.
I'm still confused. So how do you still have V cart in the equation? Because
How do you sub V cart in the equation?
how you still have the velocity of cart still in the equation, and you had to solve for, and for you solve for V cart instead of V ball.
Okay, so all you have initially is zero momentum. Then what happens is relative to the ground, Chuck is going to be moving with the cart to the left, and their momentum will be M cart times VC, but negative. Meanwhile, the ball will have a momentum M ball times V ball, which is to the positive direction. So it's positive. So if you solve this for for V, the velocity of the ball, you find the velocity of the ball is M cart over M ball times VC. So we got that. But we don't want VJ in terms of VC. We want VJ in terms of U, the relative velocity of the ball with respect to the cart. So what you're really saying is V ball is U minus V of the cart, because U minus V of the cart is really what Chuck thinks the velocity of the ball was. So Chuck thinks the velocity of the ball isn't VC, or excuse me, isn't VB. He thinks it's U because that's how rapidly it's moving with respect to him. See, if you solve this for V ball, you get V ball is equal to U minus VC. So that's what Chuck sort of sees it moving as, is that U velocity. Now, what we did is then the momentum was conserved for the ball and the her system. So the girl with the ball both make a new system, but that momentum's not initially zero. That momentum is the momentum of the ball initially. And then she catches it, which means they stick together. So it's like they have now a new mass, M cart plus M ball, and they move off with this new velocity, VJ. I solved for that by dividing by M ball plus M cart and got this, but that's just in terms of the velocity of the ball with respect to the ground.
Yeah, but
Now, I didn't want the velocity of the ball with respect to the ground. I wanted it in terms of U or VC. So I took VB, which was in terms of VC, and plugged that in there. The V ball, the M ball down here canceled out with the M ball up here and left just M cart over M ball plus M cart in the bottom times VC. Now, if I realize that U is VB plus VC, then I just have to compute that by saying it's VB, which I already found was this, plus VC, which I found is just that. But in order to get them into one term, I had to get a common denominator, M ball. So I multiplied it by M ball over M ball. That actually gave me M cart plus M ball over M ball is equal to VC, or times VC is equal to U. Solving that for VC, I got this, and that's how I got the result that they had. Does that make some sense?
So you solve for VB and just plug into the equation because it just looks kind of blurry. I can't really see. But is that a? Did you say plus M ball over MG? I mean MB, or is that
Which part are you
equal?
talking about?
The part when you say VJ is equal to M ball
This is
over. No, above. Yeah.
M ball plus M cart. Yeah, that's ball 2. I just got lazy and didn't want to write ALL.
Yeah.
And
Then
this
you
is plus
said,
down here. It's just it ran into the M.
but is that entire equation equal to that other equation with the velocity of the ball? Or did you added that
So
equation again? I
yeah,
just
now
couldn't
that I
see 'cause it
have
was
the
blurry.
velocity of J with respect to the ball, I substituted this, which is the velocity of the ball, for that VB. And that M cart ends up here, but this M ball cancels out with this M ball. So that's how I got cart over MB plus cart. Then I had to use what I found was U, which was M cart plus M ball over M ball to solve for BC, or excuse me, to solve for BC in terms of U. And that gave me this. And then when I plugged this into there, that gave me the result that they had.
Okay. Just that you solve for VB and then replace that VB with VC with the equation with VC
I
in it.
replaced that VB with the formula for VC.
Okay.
Exactly. That one up there. And that's how I got just that. Now I got to go and take this crap and plug it in there, and that gives me this. All right, so I went ahead and drew those up at the top so people can make sense of it. You have any other questions, Lauren?
Pretty much it for right now.
Rosa, did you have any questions, or are you just sort of not there? Can you type in a chat message, Rosa, if your speaker's not working? I don't think she's there. I'm going to go ahead and...
I may have some more questions later on other problems, so I'll just email you them.
Okay.
I pretty much
keep going, chucking. You'll get there.
Yeah, I kind of rushed with the chapter 9 homework from it being done like really quick, because I'm so used to doing like the conceptual before the homework, because the conceptual kind of pretty much
Right.
you can practice with, and it
I
kind of
did
like
make the conceptual
learn that.
due before the problems, but I moved the deadline back a little bit so they were the same. So it was originally set up for the concepts to be due before the problems, but now they're both due some time from now. I think I have the concepts due on the 31st, and I believe I have the problems due on April 4th. But you really should, obviously get your concept questions done, then start taking the practice test. Do a bunch of those, maybe even before you finish the homework. But I'd probably try at least all the homework problems before you start jamming on the practice test. Because if you, I just don't think you're going to be as ready for the practice test until you've done at least attempted all the homework problems. Okay. All right. Well, I'm going to start prepping for my next class, so I better let you go, bud. Send me an email if you have any questions. You got anything else for our split, though?
That's it. I just seen your email if I have any more questions.
Okay, thank you, bud. Have a good one.
All right.
Don't forget to do your test.
Okay. You have a good day.
Have a good one. Bye-bye.